Alright, so what I'm going to do here is perform a hypothesis test of the mean. We are going to use the traditional method for a z-test. I will make another video where I do a p-value z-test, and then later on we may do a t-value test, but not on this video. So let's go ahead and read through it and then take the information out that we need in order to perform the test. A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. She selects a random sample of 36 four-year public colleges and finds the mean to be $5,950. The population standard deviation is $659. Is there enough evidence to support the claim at the alpha level 0.05? Now, we are going to be doing hypothesis testing, which means that we are going to be comparing two different thoughts. Now, our first thought is that there is no change, and it's always going to be that way. So, my null hypothesis, meaning that there is no change, is that our mean is the $5,700. Our alternate hypothesis addresses the same thing, but it's making the statement that we believe the mean is either greater as a right tail test, lesser a left tail test, or it's just plain different, in which case it would be a two tail test. Now for ours, we're testing the claim that it is greater than the $5,700. In other words, that the true mean of the population is greater than 5,700. Now, we're doing greater than, which is a great indicator that we're doing a right-tailed test. Okay? Now, I like to identify a few more values at this point. I like to know what significance level I want, and our significance level is represented by alpha, specifically lowercase alpha, and in this case our significance level alpha is 0.05. Other things which are going to be extremely useful are, what is our test statistic? Our test statistic is the information we got after we took our sample, and from our sample we found our sample mean, our x bar, to equal 5,950. Last but not least, we should jot down whether or not we have sigma or if we have S. If we have sigma, more than likely we're going to be doing a z-test. If we aren't given sigma and we just have the population standard deviation, then we would be using a t-test. So they gave us the population standard deviation, letting us know it's going to be a z-test. So sigma is equal to 659, and lastly our sample size n was 36. Alright, so from here I'm going to perform my test. Okay, so now that we're going to do our hypothesis test, let's label our graphs the way we always would. Now remember, we're coming from two different places. We got two different things we're looking at. We're looking at our sample world, alright, and over here in our sample world we have our mu is equal to 5,700, and we have our standard deviation is 659 divided by the square root of 36, the sample size. Alright, now over here in our idealized world, alright, and remember it's our z world, the idealized world, the standardized world, alright, our mu is equal to 0 and our sigma is equal to 1. Okay, so our alpha level for our right tail test means we're shading the right side of the graph, and we're shading the right side of the graph such that the area underneath the curve is equal to our alpha level of 0.05. Right? And that's the same shaded area whether we're talking about the sample world or the idealized world. Okay, it's the percent out of 100. 5% is contained to the right of our critical value. So what do I mean by critical value? The left side, the unshaded area, is where our hypothesis, our null hypothesis, is still considered true. Everything to the right in our shaded area is in our critical region, also known as our rejection region. Now our critical value for a traditional test requires that we find what our z value is for the alpha equal to 0.05. Some textbooks give you a list of critical values for known alphas, but let's go ahead and use the calculator for that. Now, we need to find the z-value associated with that area. So that area is what we have over on the right. So we turn our calculator on, we clear whatever we have there, and we're going to go to our distributions. And in distributions, we're using inverse norm. And our inverse norm is for the area that's over there on the right. So remember, our inverse norm always counts everything from the left up to our stopping point, so really it's at 0.95 because that's all of the unshaded area. We're in our idealized world, so our mean is 0 and our standard deviation is 1. We could have found our critical x value, but that's not how the traditional test goes. The traditional test, we do all of our work in z-world, so that's why we use these numbers. Alright, and we got our z-value is equal to 1.6449. I'm rounding it at 4 decimal places. Now, if you had used our mu and sigma from our sample world, alright, you would have gotten a different number. Similarly, if you gotten the negative, that means you would have done it at 5% instead of 95%. Okay, so from here, let's actually place what we do know on here. What we are doing with the hypothesis test is we're going to test out our null hypothesis versus our alternate hypothesis. Why am I putting 2 lines on here? Well, I don't know if x bar, right, which is 5,950, lives in the critical region, right, in the shaded region on the right of whatever that critical value is, or if my test statistic lives in my non-critical region, my do not reject area. So I now need to take my x value and move it over here into my idealized value. Now, if we remember our math correctly, we're going to take x bar minus mu divide by sigma over the square root of n, and that's going to give me a value of whatever my critical z value is. Alright, so now I'm going to use the calculator to do this, and I'm not going to plug in the details because now I'm going to use my test on my calculator. So hit stat, go over to test, we're doing a z-test, which is the first one, and I'm going to enter in the data. I already have it entered in, but it's statistics because it's the actual values. My mean of my population is 5,700. My sigma for my population was 659. My x bar was 5,950. My n is 36, and it's a right-tailed test. Go ahead and calculate. Alright, when I calculate it, do you see right there we have the z is equal to 2.27615? That is what our z value is for our test statistic. Our test statistic is 2.272, or let's go 17, so it's at 4 decimal places to match what we also had. Now you tell me, is the 2.271 to the right of the 16449 or to the left? It's to the right. So, looking back at our hypothesis test, which arrow matched? The arrow that was not in the critical region or the arrow that was in the critical region? The one that is in the critical region. So what I do is I get rid of that one, and I've now answered what they were asking for. There is enough evidence to reject the null hypothesis, see how I scribbled it out, to support the alternate hypothesis, which is that it's changed. So since it's about it's changing, that's what I'm going to write when I go back to my original problem. And what I write is, there is enough evidence to reject the null hypothesis, thus there is enough evidence to support the claim that the cost is greater. Remember that they addressed the claim, and our claim was that the cost for college was greater. So in my hypothesis test, when I use the English sentence to sum everything up, I have two things that I'm going to say. One is addressing the null hypothesis, the other one is addressing the claim.